Okay, so last time we talked about the balanced force particle model, and we defined a force as simply an interaction between two or more objects. We then went through different types of forces here and the directions that those forces are pointing from. Like the normal force is always perpendicular from any surface. Like if you have a book on a table, the table is the surface and the normal force will be perpendicular from it, up from that surface. And if you have an object on the ceiling, the normal force will be perpendicular to the ground, pointing towards the ground. The normal force is present at surfaces. This is the symbol for the normal force, and a typical equation for normal force is that it is always equal to the force due to gravity. When we get to ramps, we'll see that the normal force is equal to a part of gravity. Friction. Friction force is always opposite an object's motion. If an object goes right, the friction force goes left, and vice versa. It is always present on surfaces and through air in the form of air resistance. A symbol for the friction force is F sub F, as you can see there. The equations for friction force, there's two types of friction force. There's static friction, that's the friction that's going to always oppose your motion, but is going to keep the object stationary. So the amount of force that you push on an object or pull will be equal to the static friction that comes back the other way. So if you're pushing towards the right on an object, the static friction force is going to be going to the left. And if it is equal to your pushing force, then the object stays at rest. But if you provide enough pushing force to overcome the force of static friction, then the object will move under a new type of friction called kinetic friction that we see there in the second equation. That friction force is always less than static, and it is less than your pushing force, but it is present, and thus you are able to push the object in question or pull it. There's a gravitational force, and it's always towards the center of mass or center of gravity, which we will become comfortable with when we talk about center of mass and gravity. It is present in any gravitational field. Typical symbol is F sub G, and it has various equation forms. Fg equals mg, that's what we're going to be working with mostly in chapter 5. There's a tension force. It always points away from objects. We've seen that on the exam. We've seen that in some homework questions already, that the tension force is always opposite, or always points away from your objects. It's present in strings, ropes, and the like. Typical symbol for tension, F sub T, and there's no real equation for tension. It depends on what force is going the opposite direction of tension, that you can create an equation for tension. There's a spring force. The spring force is generally anti-parallel to your motion. So I gave the example of hanging a mass on a spring. If you pull your mass down, the spring force is going to go the opposite way every time. And if your mass on a spring goes up, the spring force is going to go down. It's always going to be opposite or anti-parallel the motion. And we'll see that the spring force is typically referred to as a restoring force because it's always trying to restore the system back to balance, back to equilibrium. It's present in springs, rubber bands, elastic stuff, and symbol for a spring force, F sub S. And the equation for spring force, F sub S equals negative K delta X technically, because delta X is a displacement from 0. And K is the spring constant. Spring constant just tells you how strong the spring is. Some springs are stronger than others. Then another type of force is the magnetic force, or also called electromagnetic force, because they're coupled. The electric force and the magnetic force coupled with each other in the electromagnetic spectrum. The magnetic force is perpendicular to both the magnetic field and the velocity of the charge in question moving in that field. So if you have a proton or an electron, the magnetic force is going to be perpendicular to the speed of that proton and electron, and also perpendicular to the magnetic field. So we have the magnetic field and the velocity are going to be perpendicular to each other, and the magnetic force is going to be perpendicular to both of those. So we have a three-dimensional system happening there. The magnetic force is present in any magnetic field, and the symbol for magnetic force F sub B. The general equation for magnetic force F sub B equals Q for charge, proton, electron, velocity, cross magnetic field. So these two vectors that form a cross product of each other will form a magnetic force, or a new vector. In this case, the vector of magnetic force.
Mr. Kelly?
Yes.
You weren't writing or scrolling down, are you? For me, it's still stuck at the top of the screen.
Well, I'm scrolling now. Can you see that?
No, I can't. It's not moving.
Oh, okay, so let me stop this share and reshare. Yeah, because I know it was stuck there. Can you see it now? Okay, so I knew it was coming. I just didn't know when. All right, can you guys see things now?
Yes, we can.
Okay.
I think.
Yeah, you see me scrolling?
Yeah, it's good.
All right. All right, so last time we talked about Newton's laws of motion. We talked about Newton's first law and Newton's third law. An object that rests remains at rest or constant velocity unless acted on by an outside net force, an outside external force, net force. And the object will be in constant velocity like this in terms of the CVPM, because we know CVPM, constant velocity particle model. But if we have an outside force that's going to disturb that constant velocity, then that force will be an unbalanced force. And then we go to Newton's second law. So Newton's first law is a law of rest, a law of equilibrium, a law of inertia, the tendency to remain at rest. That's what inertia is all about. We talked about that the other day. Inertia is the state of being at rest, if you will, or being in equilibrium. You're not going to easily move an object the more inert that object is, meaning if the object has a lot of mass, the tendency to be moved is going to be very hard because it's really very massive. It's really very large. And Newton's third law, for every action, there's an equal and opposite reaction. So it always involves two objects. So the force of the first object on the second object, whatever that is going to be equal and opposite the force of the second object on the first object. You put your foot on the ground. So the force of foot on ground, if your foot is the first object, the force of foot on ground is going to be equal and opposite the force of ground on your foot, the other way. And they will always oppose each other. So even though those forces are equal, the object with less mass is the one typically seen moving. So you're going to be the one moving as you walk across the floor. So we're getting a little bit into these system schemas. Basically, the system schema is just a way of brainstorming the forces that are being applied to a particular object. But we've gotten past that to talk about the free body diagram. So the system schemas, okay, what kind of forces could be acting on a particular object in the schema, and then the free body diagram just talks about the objects that actually are acting on the object. So we'll do a little bit of that in the next block. So like I said, Newton's first law, law of equilibrium, it's the two conditions for equilibrium are a condition of rest or condition of constant velocity. When you have those two conditions, the total amount of forces acting on that object, the total amount is equal to 0. So we saw that the net force is going to be equal to forces in the horizontal direction, the vertical direction. You add those two forces together, they're always going to be equal to 0 for the system to be at rest or to be at a state of balance. Newton's second law, now we have an outside net force that's going to disturb the balance. It's going to accelerate the object. So now F net is not going to be equal to 0. It's going to be equal to mass times acceleration. It's the second law. And then we also stated that if we solve for acceleration here, and if your object doesn't have a lot of mass, it's going to be accelerated to a large degree. The acceleration is going to be large if it's got a small mass. And conversely, if we have a large mass, the acceleration is going to be small under the same force. So this is just another way of seeing Newton's third law. Even though the forces are the same for both objects, the one with less mass is going to accelerate more. It's just an inverse relationship. And then again, Newton's third law, force of 1 on 2 is equal to negative F2 on 1. Force of object 1 on 2 is equal and opposite 2 on 1. And if we just, like I said before, if I had the foot on the earth, the force of the foot on earth is equal and opposite the force of earth on foot. All right. So I think we get that point. Now going to the next page of the worksheet, let's kind of just, work our way through this first section. And then I'll be giving you homework for the other pages. So let's talk about this. So take care in reading every word in these questions. Make sure you know exactly when we are taking our snapshots in each part of the problem. When making a whiteboard, arrange your work so that all parts of one question can fit on one board neatly. Now we're not going to be making a whiteboard in this sense, because this was generally a project that you can do. You can do forces and free body diagrams and then put it on a whiteboard and then present it before class, but we're not going to be doing that here. So we're doing something not so widespread. So question 1, we have a cardboard box with a rubber bottom, contains a cinder block at rest on a rough concrete horizontal floor. Now, what we want to do is draw a system schema for this situation. So the system schema is basically you brainstorming all the possible forces that could be acting on this cinder block. So if you will, we could say that, the schema usually has like you can have a dotted circle and say, okay, we want to label all of the forces that could possibly act on the block. Okay, question. Oh, okay. Yeah, I don't see him. Okay, so now in the system schema, let's figure out all of the forces that could be acting on the block. And before we connect any dots, we just label all the different forces in actual circles. So we can say, all right, so the block is it's sitting on the floor. So the rough concrete floor could be acting on the block. What other forces could be acting on the cinder block? So it's sitting on the floor. Any other contact forces or field forces? Go ahead.
Gravity.
I'm sorry?
I said friction and gravity.
Yeah, so the friction due to the floor, and then we can also say the force of gravity. Okay, anything else that could be acting on the block? That's pretty much it, right? Because it's just the cinder block. We can just draw a quick picture. It's sitting on a piece of rubber, and if we just have the block here, and here is the floor. And usually this phrase rough or has friction, that usually implies that there's going to be, obviously there's going to be friction in the system. So this is our schema. So basically we have isolated the object that we want to lay the forces on. And then the circles here just are the actual forces that could be acting on the object. And so what we do in this case is we just draw lines to the forces that are in contact or acting through a field on this block. So there's one contact force. It's the force due to friction by the floor. And then there's one field force due to gravity. We can leave out air because it's just sitting there. The air is not really, doing much in terms of a force on the block. So this will be what would be the schema. So it's just a brainstorm for your free body diagram. That's all it is. So in most of our problems, as we see in our homework, we won't even need schemas. This is just a way for you to understand that it helps you label the type of forces that are acting. Okay. So in the second part, since the shape of the box plus cinder block, your system, is unimportant, shrink it to a point. This is where we are treating the box like a particle, and then show and clearly label each force on the system. Make it obvious in your diagram which forces you intend to be equal and which you intend to be greater than others. Does rubber, we're going to treat the block rubber system as one thing, as we see in the second part B. So short answer, not really. We're not going to treat the rubber as separate. So the box cinder block system here, okay, is going to be reduced to a particle, right? That's what we've been doing so far with our free body diagrams. So now we're just going to translate the schema into an actual free body diagram. So the box is here. We know that the floor is going to, since it sits on the surface, this is the floor here. The normal force is going to be perpendicular from that surface. So we have a normal force that points up, perpendicular up from the surface. That is a contact force. And then we also have the force due to gravity. And since it's just at rest on the floor, we're not going to put friction in the system because friction is just, that force there is only going to be active when we're trying to push or pull the object. So right now it's just at rest. The floor is rough, yes, but we're not going to be worried about friction right now until we start to push it. Okay, so any questions on part B? Okay, so moving along. Now for part C, a person shoves the box horizontally so that it begins to move. So now we're going to see that friction comes into play. Because now we're going to start to push it, let's say to the right, and friction is going to go the opposite direction. Your answers to this part should concern the time while the person is still touching the box and shoving. We want to draw a velocity versus time graph for the box, clearly marking the time when the box is at rest and the time when the person is still touching the box and shoving it. This should be qualitatively accurate, no numbers, but correct shape. 2, also draw a system schema for that same time period. 3, also draw a free body diagram for the box during that same time period and label. Okay, so first thing we want to do is draw a velocity time graph. for the box. So the time when it goes from being at rest to motion. So velocity time graph like that. So we're clearly marking the time when it's at rest and time when the person is still touching the box and shoving it. Okay. So before we get back to that, let's draw our system schema. So again, the block center block system, the box center block system is the object in question of which we want to label, we want to get all the forces that are acting on. Okay, so let's see, we have block here. And then, just as we mentioned before, it's sitting on the floor. The floor exerts a normal force perpendicular from the surface. It's always up from the surface. So here's our surface here, pointing upward. And if it was, again, if it was on the ceiling, it would be pointing this way, normal force. And also gravity would be there as well, because that points down. So the block is on the floor, normal force points up. We are trying to push the box. So there's another contact force of the push. Since we're trying to push it, there is, let's squeeze things here. The force of friction there. And so we're not connecting anything yet. We're just brainstorming, trying to get all the forces that are acting on the block. Normal force, push, friction. I'm missing something.
Gravity?
Yep, force of gravity, always there. And so even though that's a field force, these other three are contact forces, we're just going to draw a line connecting all of the forces in contact or acting through a field like the force of gravity. So like we did before, system schema, something like that. And for the most part, we'll ignore air resistance, although you could put that somewhere out here, but it's not really in direct contact, so it doesn't matter. So that's our schema. And free body diagram would be next. I'm gonna squeeze it right here. So again, object in question is represented by a particle. Let's say I'm trying to push it to the right. Just getting it to move. So my friction force is going to be to the left. I can call it negative FF. Or if my FP was to the left, it'd be negative FP and positive FF. Normal force and force through gravity. Okay. So velocity time graph. So I mean, it just starts to move. So we could say that for a small unit of time, the object's at rest. So its velocity is equal to 0. And then we just get it to move. Like we could keep it either this way with velocity is equal to 0, but since they say just that it begins to move, we're going to give it a slight shove, right? So it's going to have, it's going to be accelerated from velocity equal to 0 to some non-zero velocity, right? So this is my VT graph, meters per second. You know, you can, if you have space, you can put your meters per second there and time in seconds. So that pretty much answers that question. Any questions on that? Draw velocity versus time graph for the box, clearly marking the time when the box is at rest. And we don't, you know, again, we don't have to, you know, no numbers. So just some arbitrary time t here, you know, t1, you know, whatever. Okay, now for part D. The shove ends when the box leaves contact with the person's hands. So we're gonna do the same thing, VT diagram, schema, as well as the free body diagram. Draw a qualitatively correct velocity versus time graph for the box, clearly marking the time when the box is at rest, the time when the person is still touching the box and shoving it, and the time after the box loses contact with the person's hands. Okay. Make it obvious which lines are horizontal, which have greater slopes, smaller slopes, or negative slopes. So as I'm introducing this to you, we're going to treat friction obviously a lot more comprehensively when we get to that subject. But this is just an introduction to the concept. Okay, so we have a VT graph, looks something like this. All right, so the object's at rest for a certain time t1. Like before. So we can say that, okay, it's at rest. It's being pushed, but the object hasn't started to move yet. Here we can say, okay, it starts to move. So it's now, you're pushing it and the object is going from 0 velocity to some non-zero velocity. 2 meters per second, 3 meters per second, whatever. Now the deal with friction is, once we lose contact with the box, what do you think friction is going to do to the box after I lose contact? This is something, you know, I'm sorry?
I was saying, yeah, Nicole was saying it, like resist like a motion of the thing so it doesn't, so the box doesn't move forward or wherever pushes.
Yes, the main idea with friction, its sole job is to bring an object to rest. It's to decelerate the system, because as you can see here, if my object is going to be moving to the right, I'm pushing it and I'm making it go to the right and I lose contact, then as the object is going to the right and friction is going to the left, friction is going to slow the object down. Its main job is to bring it to rest. So I'm going to just write here that I'm in contact with the box, then I lose contact and friction takes over. It's going to then bring the object back to rest, either immediately or some kind of time interval. Because once I lose contact, there's going to be an unbalanced force of friction that points to the left. And that friction force is opposite your motion. That friction force is going to cause the object to slow down to a stop. That's what's going on in that scenario. So I have a contact from T1. Let's say that this is T1. This is going to be T1 to T2. And then from T2 to T3, I've lost contact and friction takes over. Friction is going to slow the object down to a rest. Back to rest. Okay. So if we were drawing a system schema, the box would be the important object. And what we want to do here is we want to label all the possible forces acting on the box: a normal force, force due to gravity, friction. I'm not concerned with air resistance. But this schema only works when I've lost contact. Friction is present, force due to gravity, and the normal force. So I'm just going to go ahead and draw arrows on those forces that are in direct contact or through a field with the box. So this is going to be important for when I lose contact. But obviously when I'm in contact, I have this situation up top. So don't have space per se for that. But when I'm in contact, you can just draw another force, which is the force of your push. Okay, so when I'm in contact with the object, I'm just going to squeeze this here. Normal force, force due to gravity. And since I'm able to move it, my pushing force is going to be greater than the friction here. In this case, the force of friction is going to be due to static friction. Again, we're going to do this here and we're going to go forward to friction down the line and really treat it better than this comprehensively. But right here, the friction force is static because it's not moving yet. Now that I'm still in contact with the box and it's moving, there's still friction force here, but that friction is less than my pushing force. That's why I'm able to push it. I now have an unbalanced force that causes me to accelerate the object from rest to some non-zero speed. That's my contact. That's my free body diagram for contact. And then my free body diagram when I lose contact would be something like this. Still on the floor, normal force, force due to gravity, and I have kinetic friction or just friction force. Because it's a rough surface, it's still going to have friction there, but it's the moving friction or kinetic friction. So notice that I don't have my pushing force there because I've lost contact. So this is my free body diagram for losing contact, and then it comes to rest. Maybe a lot there, but any questions on that?
So essentially, the friction after you lose contact will always be in the opposite direction of the direction you pushed?
Yes,
Okay.
always. Right, and I'm just choosing to go right. If I go left, then friction is going to go right. That sort of thing. So I'll leave the rest for some homework down the line, but I wanted to make sure that we got that. Any other comments, questions on the other parts? So I think what I'll have you do, I mean, not for homework, because you have homework already due Wednesday. I'll have you do a couple of sheets of the packet. Yeah. Okay, so why don't you, you can try question 2. How about we do that for 10 minutes? Yeah, you can just stay right there if you want to. Well, yeah, I'll just put you in your breakouts, breakout rooms. And so for 10 minutes, I want you guys to do question 2, and then we'll come back and talk about it. Okay. Does that seem good? T1, T2, T3. I'm shoving but not moving for T1. And let's see, let me get that question up. Would the velocity without the rubber stopper be higher than with it? It would actually be less because now you're in direct contact with the floor, which is of a rough surface. The rubber actually eases it a little bit, makes it faster. But more on that down the line. So the 3 time intervals, we are shoving, not moving, T1 to T2. I'm in contact, but my pushing force is greater than friction, which allows me to accelerate it, increase its speed from 0 to whatever. Then I lose contact and friction brings it to rest, from T2 to T3. Okay. Moving along, so let's do our system schemas. So the object in question is our box, dotted circle there, and and then we have normal force in contact, and then we have the force of gravity. This is at rest, so we're just basically taking the stuff from question 1 and putting it all at once in question 2. We have a normal force here and force of gravity. That's all we have while the box is at rest. System schema and an FBD for the situation while the person is still touching the box and shoving. Okay, so there's a couple of options here, but I would just take the easy, simple route. So this is our system schema for the box. You have normal force, force of gravity, the only field force here, force of friction. We don't care if it's static or kinetic. And then our pushing force. At least in the schema, we don't care if it's static or kinetic, but I'm going to draw the free body diagrams for both situations I depicted here, right? Because my pushing force is going to be exactly equal to my static friction. Nothing's happening. Static, I mean, if I push forward with 2 newtons, static friction is giving me back 2 newtons. Nothing's moving. In this case here, I may have my kinetic friction to be 5 newtons and my kinetic friction to be 1. So I'm unbalanced in my direction. I'm able to push the object forward. And then, object comes to rest. At this point, under the influence of kinetic friction. Okay, so let me just draw both of those situations. So free body diagram for the static case, normal force from the ground, force of gravity, pushing force, and my static friction. This friction is going to be equal and opposite my pushing force. So everything's in balance. The normal force and gravity are equal. My pushing force and friction are equal. Net force is equal to 0. Objects at rest. Then this free body diagram here would be from 0 to T1. Then from T1 to T2, I have normal force, force of gravity, pushing force like that, and then my kinetic friction is just going to be a small amount. Any questions on that? See the differences? This would be a situation of all the forces in balance. The total amount of forces in the system equals 0. In this case, it's unbalanced because this guy is much bigger than, these two guys are equal, but these two are not. So as long as you have one force out of balance, one force bigger than the others, that it will be the direction that the object will accelerate. It will go from 0 speed to non-zero speed. All right, and so this would be from T1 to T2. And then draw system schema and FBD for the situation during the time after the box loses contact with the person's hands, okay? Again, got it for box, right? They're still on the floor, normal force of gravity, and then we'll just have friction, right? FF or whatever. Okay, so then normal, no longer pushing force here. I can just say kinetic friction or just friction force. So does that make sense there? You guys see that? Okay, so hopefully you got that on the second page. So all these free body diagrams, this is the only situation that's not represented here. The objects at rest here from 0 to T1 and T1 to T2 here, and then T2 to T3.
Mr. Kelly,
Yes.
the FK, is the K the constant for the rubber? Is that right?
No, this is a kinetic friction.
Oh, sure, yeah.
I will just call it friction force for now, because we will make the distinction, you know, more clearly when we talk more about friction. But yeah, since it's moving, the type of friction that's there is kinetic friction, the moving friction. Where is that part? Where is that? And section 5.3 talking about mass, and now we're going to continue on with that section and talk about Newton's second law. Newton's second law involves unbalanced forces. When an object experiences force, causes it to move, change its velocity. This force, this situation can only happen if there's an unbalanced force, because in Newton's first law, everything's balanced, all the forces add up to 0. 2 newtons in the positive y direction, -2, and -3 in the x direction, and +3 in the positive x direction. So everything adds to 0. But Newton's second law, there's one or more forces are unbalanced. So in that situation, it experiences acceleration, as we defined earlier. Net force will be mass times acceleration, and where acceleration is equal to net force divided by mass. Okay, also we talked about this. The larger the mass, the less it accelerates, right? Just from the inverse relationship. So large mass, small acceleration. Under some force. And the smaller mass, the more it accelerates under that same force. Okay. Again, F net being constant, large mass, small acceleration. Small mass, large acceleration. 2 Newton force will accelerate a tennis ball more than a 2-ton truck. Although the truck will accelerate slightly. It's so massive that you really can't detect it. Okay. So again, so the F net equals ma. That's basically the equation statement of Newton's second law. You can have forces, net forces, in any direction. So if you have a large net force, like with the pushing force in our example from the packet, pushing force is larger to the right, so that object's going to accelerate to the right. Everywhere else, there's no acceleration. That force, whatever direction the larger force is acting, that's what dominates the system. That's what's going to, so the object's going to move in that direction only. And so we can have force in any direction. Fx equals mass times acceleration in the x direction. Y direction. So shouldn't be anything crazy about that. Forces, as we know already, measured in newtons. Oops. Capital N. One Newton is equal to 1 kilogram meters per second squared, because mass times acceleration gives you force measured in newtons. Okay, that's going to be kilogram meters per second squared. Again, that is Newton of force. So I think I'll just leave it at that. I was going to give an example. It's going to take more than 5 minutes, but you need to see anything that I write too fast, or hopefully you guys got all that. Okay, so it can be in any direction. Sounds good. Okay, question. So sometimes in problems, it says pounds and doesn't mention whether it's mass or weight. How do we know? And the weighting machines give our masses, right? Okay, so first question. We're not going to use pounds, but just not that you mention it. I think there's one question, homework question that deals with it. If I get my conversions right, I have to look this up all the time. In terms of pounds, I think 1 Newton is equal to 0.2448. I think I get the numbers backwards. 0.2448 pounds. I think this is reversed actually. Let me, if anybody can confirm that as I look. But you generally won't have to use pounds or pound conversion only if you need to. And your question was about the weighting scales. So the weighting scales just actually measures your weight. You know, it converts it to pounds. It doesn't measure your mass actually. So but I do take that back actually, because I have a digital scale that I can set the dial to measure kilograms, which is unit of mass. And then you can take the kilograms and multiply that by 9.8 to get your weight. So yes and no. So on that. So the scale measures the effect of gravity on the mass. In terms of the pound setting, it does, because we know that there's a certain number of pounds to a Newton, but then there are those scales that I have that can also be set to measure your mass in kilograms. So it goes back and forth. So a true measuring scale to measure your weight, it should measure the effect of what you're asking. It should measure the effect of gravity on your mass. So going back to that idea, so we defined this the other day, that weight is the force of gravity, which is mass times gravity. So typically your weight scale should measure gravity's effect on your mass. Exactly. So you get your mass in kilograms, multiply it by 9.8, you have your weight. And as we mentioned, the force of gravity itself is a vector. So if you have the force of gravity is, negative 15 newtons, mass times gravity gives you negative 15, then the weight is actually the scalar. It's actually the number, which you can convert to pounds, and then you can divide that by gravity to get your kilograms, to get your mass. So this entire thing is the force of gravity but the number inside is weight, because it's just the scalar. Okay, that's all for today. So you have enough to do for Wednesday. I'll be seeing the rest of you in like 10 minutes for the office hour.